Nenomatica, where mathematics meets YouTube excellence. Welcome to this mathematics video, where we'll prove an interesting inequality. Today, we are going to prove that for positive values of a, b, and c, the following inequality holds. bc over a plus ac over b plus ab over c is greater than or equal to a plus b plus c. The key insight we'll use to solve this problem is the arithmetic mean geometric mean inequality, also known as the AMGM inequality. For any positive real numbers x and y, this inequality states that the arithmetic mean of x and y is greater than or equal to their geometric mean. Specifically, we can write x plus y over 2 is greater than or equal to the square root of x times y. Equality holds when x equals y. For our proof, we'll need a modified version of the AMGM inequality. If x is a positive real number, then x plus 1 over x is greater than or equal to 2, with equality when x equals 1. We can verify this by setting the values in the original AMGM inequality. If we let the two numbers be x and 1 over x, then the arithmetic mean is x plus 1 over x divided by 2. The geometric mean is the square root of x times 1 over x, which equals the square root of 1, which is 1. Therefore, x plus 1 over x divided by 2 is greater than or equal to 1, which means x plus 1 over x is greater than or equal to 2. Now, let's begin our proof. First, let's consider the case where a and b are positive numbers. From our modified AMGM inequality, we know that a over b plus b over is greater than or equal to 2. If we multiply both sides by c, we get c times a over b plus c times b over is greater than or equal to 2c. We can rewrite this as a c over b plus bc over is greater than or equal to 2c. Similarly, if we apply our modified AMGM inequality to a and c, we get a over c plus c over is greater than or equal to 2. Multiplying both sides by b, we get b times a over c plus b times c over is greater than or equal to 2b. We can rewrite this as ab over c plus bc over is greater than or equal to 2b. Finally, let's apply our modified AMGM inequality to b and c. We get b over c plus c over b is greater than or equal to 2. Multiplying both sides by a, we get a times b over c plus a times c over b is greater than or equal to 2a. We can rewrite this as a b over c plus a c over b is greater than or equal to 2a. Now, let's add up the three inequalities we've obtained. From step 1, we have ac over b plus bc over is greater than or equal to 2c. From step 2, we have ab over c plus bc over is greater than or equal to 2b. From step 3, we have ab over c plus ac over b is greater than or equal to 2a. Adding these three inequalities, we get ac over b plus bc over plus b over c plus bc over plus ab over c plus ac over b is greater than or equal to 2c plus 2b plus 2a. Let's simplify the left side of our combined inequality. We have ac over b appears twice, so we have 2 times ac over b. bc over appears twice, so we have 2 times bc over a. ab over c appears twice, so we have 2 times ab over c. So the left side becomes 2 times ac over b plus 2 times bc over plus 2 times ab over c. Now we can divide both sides of our inequality by 2 to get ac over b plus bc over plus ab over c is greater than or equal to c plus b plus a. Reordering the terms, we have bc over a plus ac over b plus ab over c is greater than or equal to a plus b plus c. Welcome to today's video, where we'll solve a mathematical inequality problem. Let's take a look at our problem. We need to verify the following inequality. Square root of 1 plus x is less than 1 plus x over 2, where x is greater than 0. Let's start solving this inequality step by step. First, let's recall an important inequality. For any positive value of x, we know that 1 plus x is less than 1 plus x squared over 4. This is a useful inequality that we can leverage in our problem. Our approach will be to square both sides of the original inequality. Since we're dealing with the square root on the left side, squaring both sides will eliminate the square root. When we square both sides, we get 1 plus x is less than the square of 1 plus x over 2. Next, let's expand the squared term on the right side. We know that the square of a plus b is equal to a squared plus 2ab plus b squared. So, the square of 1 plus x over 2 becomes 1 plus x squared over 4. Now, looking at our expanded inequality, we have 1 plus x is less than 1 plus x squared over 4. This inequality is true for all positive values of x, which confirms our original inequality is valid. Since x squared over 4 is always positive when x is positive, 1 plus x squared over 4 is always greater than 1 plus x. Let's see how this verification connects back to our original inequality. Since we've established that 1 plus x is less than 1 plus x squared over 4, taking the square root of both sides, which preserves the inequality since both sides are positive, we get that the square root of 1 plus x is less than the square root of the right side. But the square root of 1 plus x squared over 4 can be simplified to 1 plus x over 2. This is because 1 plus x squared over 4 is equal to the square of 1 plus x over 2. Therefore, we have verified that for x greater than 0, the inequality square root of 1 plus x is less than 1 plus x over 2 is true. This completes our verification of the inequality. Let's visualize this inequality graphically to better understand it. On our graph, the blue curve represents y equals square root of 1 plus x, and the red curve represents y equals 1 plus x over 2. As we can see, for all values of x greater than 0, the blue curve always remains below the red curve, confirming our inequality. In conclusion, we verified the inequality square root of 1 plus x is less than 1 plus x over 2 for x greater than 0. We approached this by first squaring both sides, then expanding the right side using algebraic identities. We found that the squared inequality is true because x squared over 4 is always positive when x is positive. Taking the square root of both sides brings us back to our original inequality, proving it is valid. The graphical representation also confirms our algebraic work. Welcome to this math video. Today we're going to prove an interesting inequality involving square roots. Let's look at the inequality we need to prove. We need to prove that the square root of a squared over b plus the square root of b squared over is greater than or equal to the square root of a plus the square root of b, where a and b are both positive numbers. Let's start by restating our inequality. We have the square root of a squared over b plus the square root of b squared over a is greater than or equal to the square root of a plus the square root of b. Now, let's simplify the square roots on the left-hand side. The square root of a squared over b equals over the square root of b. Similarly, the square root of b squared over a equals b over the square root of a. So our inequality becomes a over square root of b plus b over square root of a is greater than or equal to square root of a plus square root of b. Let's use a substitution to make this inequality easier to work with. Let's define x equals square root of a and y equals square root of b. This gives us it equals x squared and b equals y squared. Substituting these into our inequality, we get x squared over y plus y squared over x is greater than or equal to x plus y. Now, let's multiply both sides of the inequality by x times y. When we multiply the left side by xy, we get x cubed plus y cubed. And when we multiply the right side by xy, we get xy times the quantity x plus y, which equals xyx plus xyy, or x squared y plus xy squared. We've now reached an interesting form of our inequality. Let's rearrange it slightly. The inequality x cubed plus y cubed is greater than or equal to x squared y plus xy squared is actually a well-known result from the AMGM inequality when n equals 3. This is a special case of the general inequality that states for positive real numbers a and b, and for n in the set of natural numbers, a to the n plus b to the n is greater than or equal to ab times the quantity a to the n minus 2 plus b to the n minus 2. In our case, we have n equals 3, and the inequality becomes a to the 3 plus b to the 3 is greater than or equal to ab times the quantity a to the 1 plus b to the 1. This simplifies to a cubed plus b cubed is greater than or equal to ab times a plus b, which is exactly the form we derived in the previous step. Since this inequality is always true for positive values of a and b, and we're using x and y which are positive since they're square roots of positive numbers, our original inequality is proven. Today, we'll prove an interesting inequality involving the nth root of n factorial compared to the square root of n. Let's start by examining the problem. We want to prove that the nth root of n factorial is greater than or equal to the square root of n. This can be written mathematically as n root n factorial is greater than or equal to the square root of n, where n is a natural number, and n factorial equals 1 times 2 times 3, and so on up to n. Let's begin our proof. The first step is to recall an important inequality. For any natural number n, and any k such that 1 is less than or equal to k, which is less than or equal to n, we have the following inequality. K times quantity n minus k plus 1 is greater than or equal to n. Now, let's see what happens when we set k equal to 1 in our inequality. When k equals 1, we get 1 times quantity n minus 1 plus 1, which simplifies to n, is greater than or equal to n. This is obviously true, since n equals n. Similarly, when k equals 2, we get 2 times quantity n minus 2 plus 1, which is 2 times n minus 1, is greater than or equal to n. This simplifies to 2 times n minus 2 is greater than or equal to n. For k equals 3, we get 3 times quantity n minus 3 plus 1, which simplifies to 3 times n minus 2 is greater than or equal to n. And for k equals 4, we get 4 times quantity n minus 4 plus 1, which simplifies to 4 times n minus 3 is greater than or equal to n. Finally, if we set k equal to n, we get n times quantity n minus n plus 1, which simplifies to n times 1, which is n, is greater than or equal to n. Again, this is obviously true, since n equals n. Now comes the crucial step. We multiply all these inequalities together. On the left side, we get 1 times n multiplied by 2 times n minus 1, multiplied by 3 times n minus 2, and so on up to n times 1. On the right side, we have n multiplied by itself n times, which is n to the power of n. Let's simplify the left side. We can rewrite it as 1 times 2 times 3 times 4, and so on up to n multiplied by n times n minus 1 times n minus 2, and so on down to 1. This equals n factorial times n factorial, which is n factorial squared. Now, let's take the nth root of both sides of our inequality. The nth root of n factorial squared equals n factorial raised to the power of 2 over n, and the nth root of n to the power of n equals n. So we get n factorial raised to the power of 2 over n is greater than or equal to n. For the final step, we take the square root of both sides. The square root of n factorial raised to the power of 2 over n equals n factorial raised to the power of 1 over n, which is precisely the nth root of n factorial. And the square root of north is just the square root of n. So we get the nth root of n factorial is greater than or equal to the square root of n, which is exactly what we wanted to prove. Welcome to our math tutorial. Today, we're going to prove an interesting inequality. Let's begin by stating the problem we want to solve. Our problem asks us to prove that a cubed plus b cubed plus c cubed is greater than or equal to 1/2 times the sum of bc times b plus c, plus ac times a plus c, plus ab times a plus b, where ab and c are all positive numbers. To solve this problem, we'll use a clever approach involving a general inequality. Let's recall that for any natural number n and positive real numbers a and b, the following inequality holds. Let's apply this lemma specifically for the case when n equals 3. When n equals 3, we get these 3 inequalities. Now, let's add these inequalities together. Adding the left sides, we get a cubed plus b cubed plus c cubed, each appearing twice. Similarly, adding the right sides, we get the sum of ab times a plus bc times b plus c a times c plus a. Let's factor out the common term 2 on the left side of the inequality. Finally, let's divide both sides of the inequality by 2. And there we have it. We've proven that a cubed plus b cubed plus c cubed is greater than or equal to 1/2 times the sum of bc times b plus c, plus ac times a plus c, plus ab times a plus b, for any positive values of a, b, and c. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. Nenomatica, where mathematics meets YouTube excellence.